Welcome, focused learners, to The Explainer. Today, we're diving into a world where literally every single degree of temperature matters, but where just one wrong drop can totally destroy your very expensive hardware. Yeah, we're talking about the ridiculously high-stakes world of liquid metal cooling.
Here's the roadmap we're going to follow today. We'll start with the ultimate thermal solution, move on to choosing your metal surface, cover safe application and repasting, check out lifespan and maintenance, and finally, we'll look at the future of liquid metal.
Section 1. The ultimate thermal solution. Understanding the chemistry. Okay, let's dive into this. Because if you're a PC enthusiast looking to push your processor to the absolute limit, you really have to look at the chemistry to understand what makes this stuff so incredibly unique. See, what we're actually dealing with here is a eutectic alloy. Basically, that's a mixture of elements, specifically gallium, indium, and tin, that acts as a single compound but with a much lower melting point. Now, unlike your standard thermal pastes that rely on solid particles that kind of limit how thin the layer can get, this stuff is completely fluid. It flows directly into all those microscopic imperfections on your processor die and your heatsink. And the result? Absolutely unmatched heat transfer. It's just on a whole different level.
This specific mixture is most commonly known as Gallinstan. And if you look at the typical liquid metal composition, it is heavily weighted towards gallium. We're talking about 66%, so roughly 2/3 of the whole mix. Indium and tin make up that remaining 34%. Now, that massive gallium content, that is the absolute secret to its incredible thermal performance. But, as we're about to see, it's also the exact reason it's so dangerous.
Section 2. Choosing your metal surface. The chemical agitation. Now, what's really interesting about this slide is how your wallet is literally on the line when pairing liquid metal with a heatsink surface. There is a stark contrast in how it reacts with different materials. Take aluminum, for example. Liquid metal will completely embrittle and destroy it, so that is a massive hard no. Now, if you apply it to bare copper, you're going to see some really heavy staining and ion migration, but it's actually technically safe to use, and it'll retain its thermal performance. But if you want the absolute best, safest surface, you want nickel-plated copper. It acts like a diffusion barrier, and you really only get some minimal cosmetic staining.
You're probably wondering why aluminum is such a hard no, right? Well, thermal engineer Der Auer actually pointed out that gallium easily penetrates aluminum's protective oxide layer, which makes it super brittle. But here's a terrifyingly fun fact for you. Aluminum also reacts heavily with water, so if you have aluminum dust with no oxide film, it is extremely explosive. Seriously. Mix the wrong metals here, and you aren't just getting terrible cooling. Chemically speaking, you're creating a highly volatile situation. Please, for your own sake, keep the liquid metal away from the aluminum.
So why does bare copper get stained so heavily by comparison? Well, it all comes down to electromechanical potential. See, gallium has a negative potential while copper has a positive one, and this difference actually causes the gallium to migrate and permanently pleat itself onto the bare copper. You literally cannot clean it off. But here's the crazy part. Even though it looks like a complete chemical disaster inside your machine, testing shows that the copper heat spreader totally retains its incredible thermal performance anyway.
Section 3. Safe application and repasting the bomb defusal sequence.
Honestly, you should treat this phase less like casually building a PC and way more like a tense, high-stakes bomb defusal sequence. Because this fluid is highly electrically conductive, precision is absolutely everything. First up, you've got to thoroughly clean the old paste with alcohol. Second, you absolutely must protect the surrounding surface-mounted devices, the SMDs. Third, apply a tiny, pin-sized drop. Trust me on this, if you squeeze out a massive puddle, you've already failed. Fourth, you're going to spread it evenly using a lint-free cotton swab. Just apply gentle pressure until you hear this soft, squishy noise. You're basically looking for a mirror-like silver coating. And finally, step 5, the vertical test.
Which brings us to a rather anxiety-inducing question. How can you be absolutely 100% sure your extremely careful application isn't just going to leak out and short-circuit your motherboard the second you move your machine? What exactly is this vertical test?
The answer is nerve-wracking, but it is totally necessary. You basically tilt your laptop completely vertical, a full 90 degrees, and hold it there for 60 solid seconds. What you're looking for is to see if the liquid metal gathers to one side and drips off. This effectively simulates your laptop bouncing around in a backpack. Look, it is infinitely better to have it spill right now while the case is open and you can easily clean it up, rather than having it silently drip onto your motherboard during your daily commute.
When it comes to all of this, physical containment is your best friend.
You must protect those SMDs with Kapton tape or a special shield coating, and this is crucial. Do not mix or layer different insulation materials. Doing that can cause uneven mounting pressure, which will totally ruin your cooling performance. You'll also want to use sponge border barriers around the chip. Oh, and here's a pro tip. Always paste a thin layer of liquid metal onto the heatsink chip imprints too. That just guarantees there is zero gaps when you screw it down. And if you do spill, only ever clean it up with 75% isopropyl alcohol and a completely fresh swab.
Section 4. Lifespan and maintenance. The amalgamation clock.
So just how long does this ultra-high-risk thermal solution actually last before you have to crack it open and do maintenance again? Well, looking at the timeline, year 0 is your fresh application. But depending on your device's operating temps, your reapplication window usually kicks in right around the 1-year mark. For super high-performance devices that run incredibly hot, repasting every 1 to 2 years is standard. By year 3, you're hitting the absolute maximum lifespan before severe thermal degradation sets in.
So the crucial point is understanding exactly why it degrades over those 3 years. See, standard paste, it simply dries out over time. Liquid metal doesn't do that. Instead, it undergoes a process called gallium diffusion, or amalgamation. Over time, the gallium actually reacts with the copper or nickel surfaces and forms this solid alloy crust. It essentially bakes itself into a hardened, restrictive layer that drops the liquid metal's conductivity right down, which means your temperatures are absolutely going to start spiking.
Section 5. The future of liquid metal. Engineering away the flaws.
So far, we've seen the incredible performance, but we've also seen the genuinely terrifying risks. Fortunately, cutting-edge chemical engineering is actively working to engineer away these exact physical flaws right now. Enter a brand new innovation, LMPMPs, or liquid metal pastes with metal particles. Researchers are synthesizing these by literally introducing gallium oxide directly into the liquid metal alloys. By combining the liquid metal with solid metal particles and stirring it with a very specific impeller process, they're creating a hybrid material. And the best part, it acts way more like a stable paste than a dangerously runny liquid.
And this brilliantly illustrates why these new features offer a massive sigh of relief for anyone worried about destroying their rig. This new paste solves some huge inherent problems. First, it controls the bond line thickness, meaning you get the exact right gap between your chip and your cooler. It also drastically enhances surface wettability and adhesion, so it actually stays right where you put it. It introduces a shear-thinning high viscosity, making it super easy to apply but remaining totally stable once settled. And best of all, it totally prevents catastrophic pump-out, keeping your expensive motherboard absolutely safe from runaway conductive fluid.
Which brings us to the ultimate question for you, the focused learner. Knowing that standard liquid metal requires such incredibly precise, anxiety-inducing application and maintenance, are the unparalleled thermal gains truly worth the catastrophic risks for your specific rig? Or are you going to play it safe and wait for this next generation of liquid metal pastes to hit the mainstream? It's a really high-stakes choice, but hey, now you have the knowledge to make it safely. Thanks so much for joining me on this explainer, and I'll catch you in the next one.